Great. So let me start by just thanking James and the other organisers for this chance to speak to you today. So I'm going to talk about pump depletion in squeezing from parametric amplification. So this work was done in the Centre for Quantum Computation and Communication Technology. So where I'm going to go is I'm going to tell you about a way of putting pump depletion into the model for squeezing. I'll say a little bit about the physics of this and why some of the terms are sort of inevitably have to appear. And then I'll tell you about something useful you can do with this. Okay, so squeezing from parametric amplification looks like this. You have a pump at second harmonic, which down converts photons into a signal and an idler mode like this. And this is the unitary that's used to describe it. This leads, if you act this on the vacuum, to the classic two-mode squeeze state, or more generally, you can represent the evolution in the Heisenberg picture by these nice closed-form simple equations. So this model is sort of the workhorse of quantum optics over the years, and thousands of papers have been written about quantum information applications of this sort of thing. But of course it's unphysical because we have photons ending up in the signal and idler, but the pump just stays the same. It's not depleted. So what we really need is a Hamiltonian like this, where the pump is treated quantum mechanically as well. And then the pump will evolve as it goes through the system as well. So this has been known for a long time, and generally this is solved, has been solved in the past numerically or through a sort of brute force perturbation type approach. The problem is that you can really only get to a pump photon number of about 50 or so before you run out of steam with those ways of doing it. So what we've done recently is found a clever way to do the expansion which retains, you can have the pump at any power you like. So when you do this, you get expressions like this. So this is the evolution of the signal mode, and you can see the normal terms that appeared in the undepleted case, and then you get these new terms. So this is to first order in chi appearing, and you can do this for the idler as well, and for the pump, and you get all these new terms turning up. So it's the pump that I'm going to concentrate on going on. So this is to first order in chi. You can do it to second order as well. Things get a bit nastier, but it's still tractable. And you can look at how this affects the output noise on the pump or the two-mode squeezing and stuff like that. Okay, so now I want to show you that there's a very simple argument for why those terms were appearing on the pump output, which is just basically a consequence of energy conservation. So to simplify things, I'm going to go to the degenerate case. So now the signal and idler are in the same mode, which I'll call A. So this is like single mode squeezing. So we've got energy conservation just tells us that the number of photons in the pump plus half the number of photons in the signal, because they are at half the frequency, must equal the same thing at the output. So if the pump has a large amplitude, we can linearize, and I'm assuming the amplitude is real here, and then we get terms like this for the C dagger C, which just becomes alpha squared plus alpha times the amplitude fluctuations of the pump. And a similar thing on the other side of the equation. So then you just reorganize that and you get this prediction that the fluctuations of the pump at the output should just be the fluctuations at the input, but then displaced a little away from the zero mean by the difference between the output photon number and the input photon number. So this is obviously a nonlinear effect. It's the pump amplitude is being displaced by the signal photon number. If we go to the full equations that came out of this expansion, we are interested in these ones in yellow for the amplitude quadrature, and you'll just have to trust me that these do in fact, if you sort them all out and go to the degenerate case, they do in fact become these terms here. So this is kind of interesting, but there's a little bit of an annoying thing. That's this alpha here. So that's the pump amplitude. So typically that would be very large. And the larger you make it, the smaller this term is. And this is why the undepleted pump theory works so well in the lab. That term is coming from here, where we have these terms with chi on chi dash, and chi dash is just alpha times the intrinsic nonlinearity, and so that's why they cancel out and you get this one on alpha. Okay, so now I want to talk about something, a useful effect that you might get out of this system. I think there's lots of interesting things that can arise from looking at these equations, but this is one we've been looking at. So as I said, the amplitude fluctuations get suppressed by the amplitude of the pump, which is a bit annoying. But if we look at the phase fluctuations of the output pump, they are the ones that they're these yellow terms here are the ones that will be important. Now these terms, you can argue they have to be there as well in order for the commutation relations between the pump and the signal and the idler to be satisfied. At any rate, we notice that these ones only scale with chi. They don't have this annoying chi dash thing. So in the degenerate case again, we find that the output phase fluctuations of the pump are the phase fluctuations of the input, but displaced by, again, this nonlinear term, and which it just scales by chi. So this is the intrinsic nonlinearity of the crystal, and so I can have any pump amplitude; it doesn't matter. And so this is a useful regime to be in. So what can I do with this? Well, let's also measure the signal output. And we're going to measure it at a particular quadrature angle theta. So it just means instead of measuring exactly amplitude or exactly phase, we just rotate to a particular angle in between. So that angle is picked dependent on the squeezing parameters of the crystal. But anyway, you'll just have to trust me that you can do this in such a way that when you square that amplitude, you get an expression like this, with this a scaling term out the front, which again depends on the angle theta and the squeezing. So the interesting thing is that if you now do a correlation between these, so we take our phase fluctuations that we've measured and the square of our quadrature of the signal scaled and add them together, then the correlation signal now has the photon number of the input displacing the phase. Now, typically you'd be pumping with a coherent state, so this would be shot noise, and if chi is small, then that's going to be much bigger and it's going to swamp this discrete signal here. and you won't see anything. But what you can do is squeeze the input pump phase quadrature. And if you squeeze it strong enough, then this will become a very small, the variance of these fluctuations will become very small. And so then you will see discrete jumps in this correlation signal that are proportional to the photon number of the input signal. So let me show it as a picture. So the idea is we have some signal input that we want to measure the photon number of. So we pass it through this nonlinear crystal with a strongly phase squeezed pump. We measure both the phase fluctuations of the pump and these quadrature fluctuations of the signal. We do some classical electronic post-processing, and we get a signal that is proportional to the photon number of the input signal. So you might say, well, we've got photon counters. Why are you going to all this bother to count photons? The point is that quadrature measurements are very fast, and they can be very efficient and broadband, and they can work at room temperature. So this could be quite a powerful device. Okay, I'm almost finished. I'll just mention related work to this that also recently came out from, among others, Hideo Mabuchi at Caltech. So this is a related system. It's a parametric amplifier again, but in this case, it's operating far-off resonance. And they can do similar things. Arguably, you could say that this system is more versatile than the one I just described. On the other hand, arguably, it's much harder to realise experimentally. That's it for me. I hope I'm basically on time. I just introduced Wanli Xing, who was my collaborator on this work, and say thank you.
Thanks very much.
Thanks, Tim. You mentioned there's the conserved quantity you put up, but there's another conserved quantity that commutes with that, which is the phase of the pump minus half the phase of in the degenerate case, half the phase of the signal. It seems to me that's what's imposing that final relationship for you in the end, because that's why you turn to phase quadratures as a way of getting access to that phase correlation. Is that a way to think about it?
Yeah, I haven't thought about it that way, but that's true. You see the coherence of the signal coming out as those a dagger squared and a squared terms. So that's probably right.
Okay, so it's a bit like an EPR state, that it's a simultaneous eigenstate of those two commuting conserved quantities.
Yep.
Okay.